Hi, my name is Ryan Sipos, and this is a preliminary design review for the Subsea Illumination LED modeling project for OPTI 485 Illumination Engineering. The United States Navy utilizes subsea remote operated vehicles to identify and destroy submerged explosive mines in littoral coastal ocean waters. These ROVs are equipped with complex and expensive sonar, locomotion, and camera systems. Once the operator confirms a target, he guides the vehicle into the mine to neutralize it, destroying all of the expensive ROV hardware in the process. In addition, the water in which the mines are located is turbid, limiting these operations to daylight hours. Existing basic illumination systems for the camera on board the ROV often result in backscatter from the particles suspended in the water, flooding the camera sensor and making target identification and acquisition extremely difficult. More advanced systems reduce this through various methods, but they are too expensive to warrant frequent destruction. Arete Associates has approached Senior Design Team 16067 with the task of analyzing the effectiveness of various inexpensive backscatter reduction techniques and determining a combination that will improve the contrast of images taken in the turbid undersea environment. The Subsea Illumination LED modeling project stems directly from Team 16067's trade study and will utilize ray tracing software to model the camera, illumination system, and turbid underwater environment. This will both analyze and verify the data resulting from the trade study experimentation. This project will also seek to make further optimizations to the illumination system that are outside the scope of the senior design team's trade study. These optimizations will be submitted to the project sponsor, Arete Associates, in order to supplement the findings of the trade study. The preliminary goal for this project is to accurately model the test system used in the trade study, the first step of which involves modeling the LED that will most effectively transmit through ocean water while reducing backscatter. Ocean water is characterized under the Gerlov Coastal Water Classification Scale, a system that classifies different types of ocean water based on transmission at different wavelengths of light. The coastal waters being tested fall between Gerlov Class 1 or Gerlov Class 3. In this graph, the attenuation coefficients are lowest, and therefore most optimal, in the green and blue range of wavelengths. Based on Beer's law, the quantum efficiency of the camera, a contrast merit function similar to the MTF, and the diffuse attenuation coefficients from this Gerlov scale, the senior design team identified the most optimal LED to be the Luxion Rebel Lime LED. This was selected from a group of 8 LEDs of varying wavelengths and manufacturers. The next step involves modeling the LED optics. The senior design team selected a set of 10 different lens optics to test, shown here. In total, there are 5 different lens shapes being tested, with 2 different designs for each shape. Using Fred, the optimal LED will be modeled with each of the tested lens shapes. The test environment used in the trade study must then be modeled. The testing environment is comprised of a 48 by 18 by 21 inch, 75-gallon glass tank that has been filled with tap water. Known amounts of an inorganic particulate commonly used to imitate seawater is added to the tank to simulate the various lengths of Gerlov Class 3. 2 primary lengths are simulated and tested, 48 inches corresponding to the length of the tank, and 5 meters corresponding to the maximum range of acquisition requested by the sponsor. A target is placed on the other end of the tank, opposite the illumination source and the camera, which are oriented next to each other in accordance with the size requirements given by the sponsor. This testing environment will be modeled in Fred, using volume scattering to represent varying distances of Gerlov Class 3 water. The secondary goal for this project is to model a real-world system, not limited by the size constraints inherently present in a 75-gallon fish tank testing environment. This stage of the project will also involve testing further system optimizations that are not being tested in Team 16067's trade study. Such system optimizations include testing the effects of polarization applied to the camera and the LED, utilizing a polarization conversion system to limit the reduction in flux due to the polarizers, testing the effects of illuminating the target from a significantly off-axis angular position, and identifying the most optimal lens shape to use with the LED, making sure to look beyond the basic set of 10 lens optics being tested in the senior design trade study. At this point in the project, the Lumiled's Lime LED and the LED optics have been modeled in Fred, the ray pathways have been determined, and the correct output spectra of the Lumiled's Lime LED has been appropriately assigned within the ray tracing software. This table shows the current status of the project, green indicating a completed step, yellow indicating a step that is currently in progress, and red indicating a step that has not been started. Still to come in this project is modeling the testing environment and ray tracing for each LED optic, making sure to verify the results with the LED and lens optic documentation given by the supplier, as well as verifying with the test results from the senior design project. The real-world system must also be modeled, along with the various system optimizations mentioned previously. In the event that time becomes a significant issue for this project, the system optimizations may be limited in quantity or scope. The system optimization with the greatest importance is the polarization conversion system, as polarization has been shown to significantly reduce backscatter in the preliminary testing done by Team 16067. Beyond simply modeling the output distribution of an LED for a set of different LED optics, this project seeks to assist Arete Associates in the creation of a better undersea illumination system. Current standards for illumination may hold up for recreational divers, but they fall short for more advanced divers, undersea photographers, and the Navy's mine acquisition and neutralization project alike. The results from this project will serve to directly improve the standards for cheap undersea illumination, thereby assisting the Navy with national defense initiatives and potentially one day improving illumination for recreational divers. Thank you for listening.